The Earth is a mysterious place. From the deepest parts of our oceans to the edges of outer space, there is still so much we don't know about our planet. One recent discovery was the Schumann resonance. Considered by many to be the heartbeat of our planet, the Schumann resonance was only first mathematically predicted in 1952 by physicist Winifred Otto Schumann. To understand what the Schumann resonance is and how it is produced requires an awareness and understanding of some of the largest physical Earth systems, and therefore provides a neat path into understanding atmospheric macrogeophysics. I'm your host Stefan, and welcome to Geophysics Explained. The Earth is the third planet away from the center of the solar system, and at 260 trillion cubic miles in volume, it is more massive than its nearest neighbors Mercury, Venus, and Mars. Composed of silicon minerals with an iron core, and with large amounts of water present in all stages of matter, across, in, and above its hard surface, the Earth is unique among its neighbors. This is especially true when considering the rich amount of vegetation that carpets the Earth and its thick atmosphere that extends far into space, composed mostly of nitrogen and oxygen. The outer edge of the atmosphere is the ionosphere, which starts 1,000 kilometers above the surface of the planet all the way down to 50 kilometers above the surface. The ionosphere is air like the surface, but much less dense, and also ionized, i.e. charged. Above the ionosphere is the magnetosphere, a region above the Earth with no atmosphere, but with a strong magnetic field. The magnetosphere helps to protect the Earth from bursts of highly charged particles ejected from the Sun. 8 minutes after ejection from the Sun, these charged particles begin to interact with the magnetosphere, influencing and following the field lines down to the poles of the planet. When this happens, we see the aurora borealis and the aurora australis for the north and south poles respectively. During this phenomenon, the bright fluid bands of colorful light are highly charged particles interacting within the atmosphere. Really powerful solar storms can cause these particle interactions closer to the equator of the Earth and not just the poles. As ejections from the Sun press on the outer edge of the magnetosphere, field lines are warped, pressing or expanding on the ionosphere and other deeper atmospheric layers. The ever-changing nature of the magnetosphere drives the electric currents of the ionosphere, which influences weather. When charged particles accumulate near the surface of the Earth, they can form storms. At times, during storms, massive amounts of charged electrons will discharge through the atmosphere and into the ground. Lightning is created when the differently charged regions of the atmosphere temporarily equalize. Photons radiate out from the bolt, and while many of them interact with matter soon afterwards, many of them will travel outwards towards space at the speed of light. When these photons interact with the ionosphere, they refract back to Earth or towards the ionosphere again. In this way, photons can become trapped in the 50-kilometer zone in between the Earth and its ionosphere, which acts as a waveguide. This is a Schumann resonance. With each photon traveling at 300,000 kilometers per second, its wavelength equals the circumference of the Earth. The foundational Schumann resonance is 7.83 Hz, with higher modes at 14.3, 20.8, 27.3, and 33.8 Hz. The 7.83 Hz foundational Schumann resonance is the highest amplitude of the different modes. The Schumann resonance is electromagnetic radiation that is even lower frequency than radio waves. And like radio waves, Schumann resonance electromagnetic radiation is able to penetrate and travel through most materials, including your body. Modern sources of electromagnetic radiation, from 60 Hz power to cellular technology, have altered the background electromagnetic radiation that we are exposed to on a daily basis, with natural electromagnetic radiation like the Schumann resonance and its higher modes now having a lower signal-to-noise ratio than existed before modern electromagnetic manipulation. With lightning discharging approximately 50 to 100 times per second around the world, the Schumann resonance is constantly being fed new photons of energy, and therefore is a stable frequency of light. Considering the complex process that led to its creation, from high-energy particle emission from the Sun to the creation of currents in the ionosphere, the Schumann resonance is considered by many as being the heartbeat of planet Earth. Since the Earth has had an ionosphere and lightning discharges in the atmosphere, the Schumann resonance has existed. Depending on the intensity, frequency, and distribution of lightning strikes across the world, the Schumann resonance can vary in amplitude, but is always present in the electromagnetic spectrum. While our understanding of the Schumann resonance is still developing and how its unique frequency patterns influence our health and the planet as a whole, there is a potential it can be used as a diagnostic for planets with atmospheres. Perhaps with new research, we will discover the unique Schumann resonances of other planets which have their own ionosphere and experience atmospheric electrical discharges. I hope you've enjoyed this geophysics topic, and I'd be very pleased if you shared your thoughts on this or ideas for future geoscience videos in the comments below. If you liked the video, politely click the like button and subscribe to my channel. I've been your host, Stephen Burns. Thanks for watching.